Hello. So, happy morning, guys. So, this is the second, retake of the first lecture on lanthanides and actinides. And yeah, I yesterday recorded the whole video, and then only at the end I found out that the my mic I connected to speaker, what headphone wala jacket, not the speaker, not the mic jacket. So everything was lost yesterday. So, anyways, no problem. We'll redo it once again. So maybe this time it might come out even better. So the first lecture on lanthanides. Lanthanides are characterized by filling up of anti-penultimate 4F energy levels. Okay, so we have come across this energy level filling up sequence, right? 1s, 2s, 2p, 3s, 3p, and 3d, 4s, 4p, 4d, and 4f, 5s, 5p, 5d, 5f. Okay, what is after f? Is there any possibility there? We still haven't discovered any of the elements that fit into, suppose, s, p, d, f, g. No, right? We have not. Say 6p, 6d, 6f. And how do we fill this? So we go about what is the rule at a elementary level? Both the principal quantum number and azimuthal quantum number are added, and they go from lower values, and electrons are filled from lower values to higher values. Oh, what did I do? Where is this thing? Okay, okay, just let me see. Okay, fine, it's here. Sorry, guys. Okay. Okay, so this is how they are filled, right? So now coming to lanthanides, why is it called anti-penultimate? See, now first 6s orbitals are filled, then 4f, and then 5d. This is the order in which they are filled, right? So why they are what is 6s? 6s will become ultimate energy level for lanthanides. Okay, 5d will become penultimate, and 4f will become anti penultimate levels, energy level. Why this ultimate, penultimate, and anti penultimate is not based on the filling up of these electrons? This ultimate, penultimate, anti penultimate is based on the distance from the nucleus. See, even though these are filled later after 6s, but 6s is further away from the nucleus. That is why this will become the ultimate energy level. Simple, कुछ confusion नहीं होना चाहिए बस. Okay, this is about point 1. At an introductory level, what is the point 2? These are, until 1907, all 14 of them were thought to be one single element. And why 14? are why 14 lanthanides are 14 in number? Simply because s orbitals can hold up to 2 electrons, p can hold up to 6, d can hold up to 10, and f can hold up to 14. So in 1907, up to 1907, all these 14 lanthanides were thought to be one single element. The third thing fact that you need to know is they were also called as rare earths. Okay, but now that term is inappropriate as many elements are not particularly rare. Okay, one example is cerium is as abundant as copper. Fine. So the term rare earths become redundant. Abundant as copper. Okay, the word lanthanide comes from a Greek word lanthanine, which means to lie hidden. Okay, so we can now correlate with what we have understood. Okay, okay, now we'll move into, okay, so coming to the next very important thing that you need to learn in lanthanides and actinides is their electronic structure. So for that you need to know their order. Okay, it's okay you mug this, okay, or you find some acronym trick, something, you go to YouTube and find out, and whatever you want you do, it's okay, but you have to learn the lanthanide elements in sequence, and then you should know their electronic configuration. Okay, if you can understand this much, it will make your whole lanthanide actinide chapter a cakewalk. There are very few things you need to learn in this chapter. Maximum 3-4 things are there you need to learn. Okay, and in any, for any question, if you write any of these 4 points, you will get marks. Okay, I'll tell you as and when I teach, I'll tell you which are those 4 points. Okay, so come on, shall we start filling up this? The first is lanthanum. Okay, all of this follow xenon. Okay, so xenon will be common to all of this. Shall I use another color here? Okay, I'll use blue. Or is blue visible? No. Red. Okay. Xenon. There's going to be 4F. There's going to be 5D. There's going to be 6S. Right. So first, let us start filling up of. Let us learn the names. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Okay, so the short of these names are La, lanthanum, La for lanthanum, Ce, Pr for praseodymium, Nd for neodymium, Pm for promethium, samarium, europium, gadolinium, Tb, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Okay, so how do you remember this? There are a lot of tricks. The way I know, or I think my teacher thought, or I saw on YouTube, okay, when I was studying, when I was a student. So lanthanum, Sera, Priya and Pamela, Sam, Europe, Guddu, Tab, D, O, Are, Tum, AB, Luta. Very simple. Okay, I'll come to this again. Lanthanum, Sera, Priya and Pamela, Sam, Europium, Guddu, Tab, Di, Ho, Are, Tum, Ab, Luta. So this is one way you can remember, and not the only way. Fine. Okay. Among these, how are the electronic configuration? Pehli baat, all of them have a filled xenon configuration. So this is common to all of these. Xenon wala. Second common thing, all of them have 6 s2 electrons. Great. Now, among these there are 4 big brothers. What do we call? Big, okay. 4 big brothers are 1 lanthanum, cerium, gadolinium and lutetium. Okay, see, how do you remember these? Is guddu ne lace, or forget, you can remember this way. Guddu, which is GD, guddu ne lace. You remember that kurkure lace that you go and have in Pushpak agencies? Guddu ne lace luta. Okay, so these 4 elements will have 1 electron in their, oh man, why did I write here? I was supposed to write, okay, anyway, no problem. Okay, so these will have 1 electron in their d shell. Only 4 of these, you don't, just because it looks fancy, don't keep filling up. GD, where is GD? GD is 5d1. Okay, and lutetium is 5d1. Okay, only these 4 will have filled electrons in their, in 1 electron in their 5d energy levels. The rest of them, see, this lanthanum, you start with 4f0. Okay, SAR, it is 4f0, then why are you still considering it as lanthanide? So this is a starting point, it is considered. Okay, there are few which tell yes, and there are few books which tell no, but okay, chalo, you, whatever, up to your, this one you put it. Okay, so you start filling with 4f, now 4f1, next should be what, sorry, you start with 4f0, next should be 4f1 electron. Next kitna hoga, देखो 1 is there, 2 is there, 3, it is not 4f2, it is 4f3 for praseodymium. Like that only, this neodymium is 4f4, promethium is 4f5, samarium is 4f6, europium is 4f7. Again it is 7 because it is going to have half filled stability. Next it is not 8, it is going to be 9, 10, 11, 12, 13, 14 and again 14. Okay, so this is how you remember the electronic structure. Good. Among these, among lanthanides, the sum of first three ionization energies for each element, okay, are very very less. So which means plus 3 oxidation state is ionic, is trivalent, and is the most common oxidation state among lanthanides. So take that point. For lanthanides, plus 3 oxidation state is ionic, trivalent, and most common oxidation state. So which means Ln3 plus dominates the chemistry of these elements. Second, oxidation states plus 2 and plus 4, these do occur particularly when they lead to one noble gas configuration. Example, if you take cerium 4 plus, so what is the configuration is F0, so it's a noble gas configuration. So that is plus 4 oxidation state also can exist. Half filled F shell, example U2 plus and TB 4 plus. Now these are F7. Completely filled F level, YB 2 plus is F14 again. So these are, usually plus 3, lanthanum plus 3 dominates the chemistry. Plus 2 and plus 4 can exist when these lead to following three configurations. Having said that, plus 2 and plus 4 oxidation states are always much less stable than plus 3 oxidation state. Note that Ln plus 2 and Ln plus 4 are always less stable than Ln 3 plus. Okay, so this should do as a brief introductory level. Next one we will go into their size, what happens to lanthanide size. Okay, I will also share my notes so you can just go through that. So thank you, see you.